Hi, everybody. In this video, we're going to talk about exponential functions. So we have a new kind of function we're going to introduce today. Throughout the course, we've seen quite a few already, right? We've seen polynomials, we've seen linear, we've seen rational, we've seen absolute value, and so on. So now we're looking at a new function that we really haven't seen yet, and these are called exponentials. So a function whose equation contains a variable in the exponent is called an exponential function. And there are actually quite a lot of real life situations that model this. Some of them are population growth, growth of pandemics, radioactive decay, and other changes that involve rapid increase or decrease. We use exponential functions to describe them. So an exponential function f with base b is described like this. So f of x equals b to the x, or y equals b to the x. B is a positive constant other than 1, and x can be any real number. So I want you to note here that x is your variable and b is a number. So it's not, your variable occurs in the exponent only, not as the base as well. Now we call this value here the base, so that's another good keyword to keep in mind. So here's an example of an exponential function. So we have f of x equals 42.2 being multiplied by 1.56 to the x power. This models the average amount spent in dollars at a shopping mall after X hours. What is the average amount spent to the nearest dollar after 4 hours? So here we have an exponential because we have that variable in the exponent. And then our base here would be that 1.56. Now, this one's a little bit more complicated. You do have a multiplier out front, but that's okay. But you still have that kind of key core idea that you have this base to a variable where that variable is in the power. So what we can do, we can still solve these. We're going to plug in 4 here. In this case, we want to know what happens after 4 hours. I don't really need the 0 on the answer. I'm just going to write it as 1.56. And you do want to keep in mind the order of operations. Now, this is something you're definitely going to use your calculator for. So let me take out my calculator. So I'm going to work with this piece first. So I'm going to go ahead and just type in 1.56. And then this is the TI-8384 app version. And your exponent key looks like this little up caret right there. So I'm going to hit that. And then I just hit 4 and enter, and it will give me my answer. And I do highly recommend that you use as many decimal places as you can, and then round at the very end of the problem. So this becomes 42.2 times 5.92240.896. Now I can do that multiplication, and I get 249.9256581. Now, if you don't have that calculator, you can have a different calculator, and that is absolutely fine. So I will show you. So here is the calculator that came with the iPhone. Again, obviously you may not have an iPhone, but you probably have a similar style basic calculator on your phone. And if you turn at least the iPhone to the side, it will open up more keys for you, and you do have exponent keys here. So you just want to kind of practice and make sure that you understand how to use your exponent key. So here I just typed in the number, I hit my exponent key. I used the general one, x to the y, so I could type in whatever exponent I wanted, and then I got that value again. So you should have some sort of exponent key on your calculator. And now here, we do want to round to the nearest dollar. So that would be the ones place. This 9 is going to bump this up. So our answer is going to be about $250. So if this exponential function models the average amount spent at a shopping mall after X hours, then on average, when someone has been at the mall for 4 hours, they've spent about $250 at that point. Now let's take a look at some of our graphs here. And again, you're going to definitely use your calculator to help you with some of this. For your exponentials, your domain is going to be all real numbers, from negative infinity to infinity. Okay. So you can plug in any values that you want here. And we're just going to pick a few to plug in. So I'm going to graph 2 to the x power and also 1/2 to the x power. And let's see, I'll do my table for 2 to the x over here. Okay. And let's start with some positive numbers first, or I'll start with 0 and then maybe plug in 1, 2, 3, and so on. So when I plug in 0, 2 to the 0 power, you do want to remember that anything to the 0 power is 1. When I plug in 1, I have 2 to the first power, which is 2, 2 squared, which is 4, and then 2 cubed, which is going to be 8. So over here, let's see, I have 0, 1, 1, 2, 2, 4, 3, 5, 6. Let's see, 6, 7, 8. If I plug in 4, I'm going to be up at 16. So it really grows very quickly. So exponentials are used when you have really sharp increases or decreases on one side of the graph. And then you do want to plug in some negatives. So here, if I plug in -1, you want to be careful, 2 to the negative first power. That negative exponent means to take a reciprocal or to flip. So this becomes 1 over 2 to the first power, which is just 1/2. If I plug in -2, 2 to the -2 means 1 over 2 to the +2. So that negative exponent is a flipping motion. So I have 1/4. And if I plug in -3, 2 to the -3 becomes 1 over 2 to the 3, which is 1/8. So on this side, as we get more negative, we're actually getting closer and closer to 0. So our graph looks like this. So here you're going to see that your domain is -infinity to infinity for exponential, so you can plug in any values you want. But the basic exponential for the range is this one here. It is going to be above 0. So for this one, our range here is going to be from 0 to infinity. It will never touch that 0 line in general for your basic exponential. You can also transform things. So if I add in a shift, for instance, like a downward shift, then I'm going to cross the axis. But if I just have a basic exponential, then your range is from 0 to infinity with 0 not included. It's going to hug over here. So you actually have a horizontal asymptote at y = 0 in this case. So now let's try the other one. So here I have 1/2 to the x power. It's the same process. You just have to be careful with your arithmetic. Okay, so if I plug in 0, I get 1/2 to the 0 power, which is still 1. Anything to the 0 power is 1. If I plug in 1, I have 1/2 to the first power, which is also 1/2. If I plug in 2, I have 1/2 squared. So remember that square can get distributed to both parts. So 1 squared is 1 and 2 squared is 4. If I plug in 3, I have 1/2 cubed. So again, 1 cubed is 1, and then 2 cubed would be 8, and so on. If I plug in some negatives, if I plug in -1. Now, let me do this work off to the bottom for a second. So that -1 can be distributed here. So I have 1 to the -1 and 2 to the -1, and a negative exponent means to flip. So it's going to take this 1/2 and turn it on its head and make it 2 over 1. So this part comes up, this part goes down, and then it just becomes 2 over 1 in this case, which is 2. When I plug in -2, I get 1 to the -2 over 2 to the -2. And again, it's going to flip this whole thing. Those negative exponents mean to flip. So that 1 comes down and that 2 comes up. So I have 4 over 1, which is 4. And then if I do -3, we're going to have 1 to the -3 over 2 to the -3, which is going to cause us to flip everything. 2 cubed is 8, 1 cubed is 1, so I have 8 here. -3 is 8. So let's plug in our values. I have, let's see, 0, 1. I have 1, 1/2, 2, 1/4, 3, 1/8. And then on the other side at -1, I'm at 2. At -2, I'm at 4. And at -3, let's see, 1, 2, 3, I'm up at 8. So 6, 7, 8. So you have kind of the opposite idea here. For this graph. So when our base is a value that is larger than 1, then you have this growing graph. And when your base is something that's between 0 and 1, so a fraction, you have this decreasing graph instead. Your range, though, for this case is also still 0 to infinity, right? You're still going up to infinity and you're going down to that 0 line. And this one also has a horizontal asymptote at y equals 0. So these are your base exponentials. Of course, we can apply transformations. So you can shift these up and down or reflect them as well, stretch them, compress them, etc. But you're going to have this kind of same basic shape in all cases here. So for characteristics of exponential functions, I mentioned a lot of them already, but things to watch out for. And again, this is your basic exponential. Your domain is from negative infinity to infinity, and the range is from 0 to infinity. And again, this could change, obviously, if you're incorporating shifts or reflections and things like that. But for your base form, this is your domain and range. The graphs of all exponentials actually pass to the point 0, 1. So you may have noticed in the last example, both points or both sets of points had the point 0, 1 on there. You can see it here in our graph, right? 0, 1, or in our table, 0, 1. And again, this is true for all of these basic exponentials. They all cross through that same point because when you have a 0 exponent, it makes that value 1. And again, there are no x-intercepts. You're not going to touch that x-axis. If your b value is greater than 1, then you have a graph that is increasing. So it's going up to the right. It's this one right here. So here is where b is greater than 1, this graph. And then when your b is between 0 and 1, so you're looking at this graph, then you have that decreasing function. Now remember, we're only looking at positive b values here, so positive bases, and also not 1. The reason we don't look at 1 is because 1 to any power is still 1, so it doesn't fit the same kind of curve. F of x is a one-to-one function, and it does have an inverse. So if you look at either of these graphs, they pass both the vertical and horizontal line tests. So they are functions. They do have inverses. They are one-to-one. We'll talk about inverses in another video. Here for exponentials, and like I mentioned already, the graph approaches, but it does not touch the x-axis. And you do have a horizontal asymptote there as well. All right, so let me do one more set of examples here in this video, just kind of continue on with graphs. So here we're going to graph the function 3x, and then we're going to graph two transformations, 3 to the x plus 1 and 3x minus 4. So let's start with our base function first here. And again, we kind of know the general shape, right? If it's a 3, that's a larger value, so it's going to be some sort of increasing graph. But I can still plug in some points to get some more specifics. So when I plug in 0, anything to the 0 power is 1. When I plug in 1, 3 to the first power is 3. When I plug in 2, 3 squared is 9. I'm going to stop there. When I plug in 3, 3 cubed is 27. That's going to be way off my graph. And then I'm going to plug in negative 1. So 3 to the negative 1 means 1 over 3 to the first power. So you're looking at 1/3. When I plug in negative 2, 3 to the negative 2 means 1 over 3 to the second power, which is 1/9. When I plug in negative 3, I get 3 to the negative third power, which is 1 over 3 to the third power. So 1 over 27. So you're getting really small here. So let's graph our base function first. So let's see, I have 0, 1. I have 1, 3, 2, 3. I have 2, 9. So 5, 6, 7, 8, 9. And then here, I'm at 1/3, 1/9, 1/27. That's getting really close to that axis. No, not the best graph, but a little more curved. So that's our base graph. I'm going to do the same thing over here too. So I have it set up. So 0, 1, 13, 29. And just do my best to make those values on the left small here. So again, this is my base function of 3 to the x and 3 to the x. Now, if you need some review, you can look in your text again or go back to some previous videos about transformations to review all those there. If you do look at your text in the section, it does have a recap there of the transformations as well. But I'm just going to talk them out. So here, remember that whenever you have addition or subtraction, you have some sort of shift. So both of these examples are shifts. And when you have an inside change, you have a horizontal shift. When you have an outside change, you have a vertical shift. So this change here is inside because it's inside the exponent. So this is a horizontal shift. Right? It's an inside change. If it's a +1, you're actually going to the left. And we're going to go 1 unit here. So I'm going to draw that one on this side. So every single point, I'm just going to shift left 1 unit. So instead of being at 0, 1, I'm going to be at -1 to -1, 1. Here, instead of being at 1, 3, I'm going to be at 0, 3. This one's going to move over, and these as well. So that would be my g of x graph. In this case, notice that you still have the same horizontal asymptote. We still have the same domain and range. By shifting left, I haven't done too much there, right? I haven't like flipped things or rearranged anything too much. So you have that same domain and range in this particular example. But notice that you don't go through 0, 1 anymore, right? That does shift over. So when we talked about those characteristics, they're of the basic form. It's not, once you apply transformations, things could change. For this one here, I see a subtraction. This is outside the original function, just kind of hanging out on the end there. So you have a vertical shift in this case. It's an outside change. And if it's a -4, we're going to go down 4 units. So actually, I'm going to make a note here that you still have y = 0 as a horizontal asymptote. So here, I'm going to take all my points and shift them down 4. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. All right, the fraction ones are a little bit hard, so just be careful. 1, 2, 3, 4, and then these will be like this. So your graph is looking like this. So notice here that you have changed things slightly. So for the pink one over here, our domain was still -infinity to infinity, and our range was still 0 to infinity, just like the original one. But here we've changed things. Our domain is still -infinity to infinity, but now my lowest value is actually down here at -4. I'm never going to touch -4, but that we shifted down 4 units. So my range is actually from -4 to infinity now. And what happens is that horizontal asymptote shifts as well. So instead of being at y = 0, it's down here now at y = -4. So again, you had your basic information, but once you start tweaking things, if you apply transformations, it can affect your domain and range. Obviously, it affects your points. It could affect your asymptote. It really just depends. So this example here, we focused on shifts. You could also have reflections. You could also have that compression and stretching too. So all of those can change your graph in different ways. So you just want to be careful, recognize the transformation and apply it, and then look at your graph again to see if your domain, range, or any of your asymptotes have changed. I will note that you do not have a vertical asymptote here. So this graph does keep increasing, but it keeps moving right as well. So there's no stop there on the x-axis. So you only have a horizontal asymptote in these cases.